A fundamental particle is a type of particle that is not made up of smaller components. In other words, these particles cannot be subdivided or split into anything smaller. So fundamental particles are considered the building blocks of all known matter. And in the 19th century, the atom was believed to be a fundamental particle. But experiments like the alpha particle scattering experiment, and I've got a video on this in the card above if you're interested. The alpha particle scattering experiment provided evidence that the atom had a structure to it. It wasn't, in fact, a fundamental particle. When James Chadwick discovered the neutron in 1932, the fundamental particles were considered to be the electron, the proton, and the neutron. Now, the electron is a fundamental particle. It cannot be broken into smaller parts, but the proton and the neutron can be broken or split apart into particles called quarks. And these quarks are, in fact, fundamental particles. There are 6 types of quark particle, and we'll discuss their properties shortly, but a proton and a neutron are built from a combination of 2 types of quark, called the up quark and the down quark. So a proton consists of 2 up quarks and 1 down quark, and a neutron contains only 1 up quark but has 2 down quarks. Now we know that a proton has a charge of positive E, or in other words, positive 1.60 times 10 to the minus 19 coulombs. And a neutron has no electric charge. But protons and neutrons are simply a combination of up and down quarks. So this electric charge must come from the quarks themselves. An up quark has an electric charge of 2/3 E. And a down quark has a charge of negative 1/3 E. So for a proton, if we add up all the charges for the up and down quarks, we should sum to positive 1 E. And if we do this for the neutron, where we have 1 up and 2 down quarks, the electric charge should sum to 0. All charges cancel out. The 4 other types of quarks are the strange quark, the charm quark, and the bottom and top quark. Now, every fundamental particle has its antimatter equivalent. So, for example, an electron is a matter particle, and its antimatter equivalent is called the positron. We can also call this the positive electron, or sometimes we call it the anti-electron. And we covered some of this in the beta particle decay video that I did a couple of weeks ago, and I'll put this video in the card above. But all antimatter particles have the same mass as their matter particles. The only difference is they have the opposite electric charge. So for the electron and proton, the antimatter equivalent would be written like this, where the E would have a positive sign or a bar over the top. The proton would have a negative sign, the opposite sign to the charge of a matter proton, and the anti-neutron would have a bar over the top. What about quarks? Do you think they have an antimatter equivalent? Well, quarks are fundamental particles, and if you think about it, if we have antimatter protons and antineutrons, they must be constructed from antimatter quarks. And I've extended our table here with the 6 quark flavours, the up, down, strange, charm, bottom and top, and also included their antimatter equivalent. And if you notice here, all the symbols have a bar over the top of them, and their charge are opposite to their matter equivalent. So an antimatter proton is made from two antimatter up quarks and one antimatter down quark. And when we sum up the charges of this antimatter proton with the charges of the antimatter quarks, if we sum up their charges, the sum total comes to -e. And if we sum all the charges for an antimatter neutron, the charges of the quarks, the antimatter quarks, we get a charge of 0. We see here that the charge has flipped for the antimatter proton, and there's been no change for the antimatter neutron in terms of the charge. The numerous types of subatomic particles that make up our universe can be broken into two main categories, depending on the particle's properties. Any particle affected by the strong force is considered a hadron. The strong force is one of the 4 fundamental forces of nature, and it holds quarks together to form protons, neutrons, and other hadrons. Any particle not affected by the strong nuclear force would be categorized as a lepton. So this would include the electron, the muon, and their antimatter equivalents. Hadrons can be split into 2 further types, which we call baryons and mesons. All baryons are made up of 3 quarks or 3 antiquarks. So, given this fact, could we class protons and neutrons as baryons? Well, because all protons and neutrons consist of exactly 3 quarks of either the up or down variety, we can class them as baryons. All mesons, on the other hand, are made up of a quark and antiquark. And examples include the K+ meson, which is made up of an up quark and an anti-strange quark, and the Pi+ meson, made up of an up quark and an anti-down quark. So like the protons and neutrons, hadrons always combine quarks or antiquarks to give a whole or 0 charge. So we have a look at the K+ meson, and we sum up the charges, we end up with a whole number, a positive 1e for the charge. For the Pi+ meson, we've got an up quark and an anti-down quark, and this also sums to a positive 1e.